Good morning, everyone. Thank you to the organizers for the opportunity to be here. It's always a great pleasure to be back at Caltech. I was asked to speak about relativistic stellar transients and the prospective impact of ULTRASAT, which is an upcoming UV time domain survey. I'll start by explaining what a relativistic stellar transient is. In the traditional core collapse supernova mechanism, you have a hydrodynamic explosion, a characteristic kinetic energy release of 10 to the 51 ergs, and ejective velocity of 10,000 kilometers per second. But in certain rare cases, for reasons we don't totally understand, you can also have a relativistic outflow that's powered by what's called a central engine. That's either accretion onto a black hole or the rotational spin down of a neutron star. By far, the most famous example of a relativistic explosion is a long-duration gamma-ray burst, and that's being shown in this cartoon here. So in a long GRB, in the traditional model, this central engine powers an ultra-relativistic outflow that tunnels through the star and breaks out from the surface as a jet. The gamma rays are thought to be produced by collisions between material traveling at different speeds within the jet itself. And then the jet collides with the ambient medium, producing synchrotron radiation that we call the afterglow. So this picture has come together after decades of GRB observations. There are entire NASA missions dedicated to finding hundreds of these per year. But there are many basic questions about this picture that have remained unanswered. For example, what stellar evolutionary pathway makes gamma ray bursts, the structure and the composition of the relativistic jet, the prevalence of these jets in different types of stellar collapses. And ultimately, the major limitation in our ability to answer these questions is that for decades, our only way of reliably finding them has been as gamma ray bursts. But it's been predicted for many years that GRBs as we know them should just be the tip of the iceberg of a much broader range of phenomena. GRBs are very rare. They only occur in association with a special type of stripped envelope supernova called a type 1c broadline supernova. And those, in turn, as you can see on the left, are themselves a rare subset of stripped envelope supernovae, so they're very, very rare. And one possible explanation for why they're so rare is that it's not some special rare stellar evolutionary pathway, but it's just that we have a selection bias, and we've only been finding the most extreme of what could potentially be a more prevalent phenomenon. And over the years, there have been many things discovered that have been suggested to be the rest of this iceberg. But I would say that at this point, the physical origin of these phenomena and their underlying connection to the well-studied GRBs remains unclear. These are very old questions, but I hope I'll convince you today that it's an exciting time to address these questions, particularly because of developments in optical time domain surveys. So as I'm sure many of you know, until about 20 years ago, we basically had two major established classes of extragalactic optical transients. And then thanks to the advent of untargeted optical surveys, the number of transient classes proliferated. And what I'll talk about today is that in recent years, thanks to the improved cadence of our wide field surveys, we've really been pushing to much faster timescales. And these phenomena have important implications for these decades-long questions about relativistic stellar explosions. So I'll talk about the progress we've made from optical surveys, and then I'll look ahead. This field will continue to be very exciting because of the expansion of wide field high cadence survey capabilities across the electromagnetic spectrum. And I know that we'll hear a lot about these facilities today or this week at the conference. My charge is to talk about UV surveys. I know Leo will talk about UVEX, and I'll be focusing on ULTRASAT. So a brief introduction to the ULTRASAT mission. ULTRASAT is a near UV survey, a single band, 230 to 290 nanometers. It has a huge field of view of 200 square degrees. It's quite sensitive. So 5 sigma sensitivity and 15-minute observation is about 22.5 magnitudes. It's scheduled for launch in 2028 and has a nominal 3.5-year mission, but I think the limit is something like 6 years, so it could go on for longer. Because of its very large field of view, it has a huge grasp. So the grasp of a survey, which is being shown in the plot here, is basically the volume of the universe that is probed by that survey per unit time. And so that's directly related to the expected transient discovery rate. The survey plans for ULTRASAT, I'm listing here. It will do a stare, so its field of view is 200 square degrees. It will image that field once every 5 minutes, and it will do the north ecliptic pole for 6 months and then switch to the south ecliptic pole and go back in summer and winter. And then it will do some tiered longer cadence surveys. So this plan actually recently changed. So a 2,000 square degree field at a 1-day cadence and 8,000 square degrees at a 4-day cadence. There will be public alerts that should be available within 15 minutes of the observation. I want to say a bit about the US involvement. So there are 8 USPIs through NASA agreement. So NASA is providing the launch, and then an additional 7 USPIs through an agreement with the Rubin Observatory. So I'm one of the USPIs. So if you have any suggestions or questions about the mission, feel free to come speak to me. All right, so that's a broad introduction to relativistic transients and ULTRASAT. And now in the rest of my talk, I'm going to talk about 3 different phenomena. For each one, I'll tell you what we've learned in recent years from our high cadence optical surveys, and then what we can hope to learn from ULTRASAT. I'll start with what are called orphan afterglows. So these are transients that in a multi-wavelength sense look very much like gamma ray burst afterglows, except that they have no associated detected GRB. This was an early candidate that I'm showing here. It was discovered by the Palomar Transient Factory as a rapidly fading optical transient with, importantly, a long-lived scintillating radio counterpart, which is characteristic of what you expect from a relativistic outflow. So the paper on this object proposed a couple possibilities for what this could be. It could be something like a GRB, but with lower velocity for the jet, too low velocity to produce luminous gamma rays, and that is called a dirty fireball, which is a sort of hypothesized phenomenon. And then another possibility is just a basic prediction of the model of GRBs as collimated explosions, and that is that this is a jet-directed off-axis. But perhaps there are other things, other variants of this model that we didn't even expect. Now, this event was discovered serendipitously, and unfortunately, there was no redshift measurement. And so there have been intensive efforts in recent years to make the discovery of these sorts of events more systematic. So we've been working hard on this using the Zwicky Transient Facility, and I'll walk you through how this works with the most recent afterglow that was flagged with our program that Kay Ryan in the back there has been leading. So this night, 13 days ago, there were about 13,000 alerts. So that was a pretty bad ZTF night. A good night would be about 500,000 alerts. These came from about 12,500 unique sources, of which about 6,000 are probably really astrophysical. We require that a given source have 2 or more detections separated by some baseline of 20-30 minutes to get rid of moving objects such as asteroids. We have to remove as many stellar sources as possible because stars in the Milky Way can flare in ways that resemble afterglows. And then finally, we apply some cuts based on the timescale and color of the emission. And that left an amazing candidate, actually, that I think a number of people in this room are working hard on. When we have a good candidate, we immediately trigger bigger telescopes for optical imaging to confirm the color and timescale. We usually do that within about 24 hours. And then to really confirm that it's a relativistic event, you need to either measure the redshift or have an X-ray detection. If we have one of those, we then trigger a suite of radio telescopes to monitor these events over months. This has been very successful. So at this point, there are 20 afterglows that have been detected blindly with ZTF. For each one, we go back and we see whether there was an associated gamma ray burst. And in most cases, actually, the answer is yes. But we have 8 events at this point where the answer is no. These events span a wide range of redshifts, and this is a big development. So prior to this program with ZTF, there had been only one candidate orphan optical afterglow, and as I mentioned, there was no redshift measurement. I want to emphasize that these events are all going to be close to on-axis, and that's just by design. If you look for a fast transient, we can talk more about the off-axis ones later if you'd like. This immediately tells us the fact that we're not finding there's a high ratio of events with gamma rays as the ones without, that there does not exist some population of relativistic transients with a similar energy and collimation to GRBs that significantly exceeds the gamma ray burst rate. This plot shows a compilation of their light curves, so the events with associated GRBs on the left and events without on the right, and the shaded region in the background is a compilation of afterglows found in targeted follow-up observations to gamma ray bursts. Okay, so what are these events that do not have GRBs? So this is the subject of Maggie Lee's thesis. So Maggie is a PhD student here at Caltech now. This is her undergraduate thesis with me. And what Maggie showed is that it's actually difficult to say, even for our very best observed objects. So these are light curves of probably our best observed object, optical on the left and radio on the right. And the two rows are just two different models. So the top row is an on-axis 30 fireball. The bottom row is an off-axis classical gamma ray burst. And so for a single event, it's difficult to say. But given that in the basic GRB picture, the slightly off-axis events sort of have to exist, I'd probably prefer the bottom scenario. And that puts even more stringent constraints on the existence of a different phenomenon, like a dirty fireball. All right, so what will ULTRASAT contribute to this? So for an off-axis gamma ray burst, in addition to having an orphan afterglow, you expect to see fast and luminous UV emission from wider angle, lower velocity material that's sometimes called the jet cocoon. So this is a cartoon of the structure of that cocoon from a paper by Udi Nakar. And it's a very basic prediction of jet propagation through a stellar envelope. The approximate rates for ULTRASAT should be about 2 per year, out to a redshift of about 0.3. We're working on doing more detailed rate calculations and forecasting in the gamma ray burst working group, which is chaired by myself and Brad Sanko. Okay, so now I'll switch gears and talk about a different but possibly related phenomenon. These are called sometimes low luminosity gamma ray bursts, sometimes called X-ray flashes, and they're defined in the following way. So gamma ray bursts follow this trend in isotropic equivalent energy on the x-axis and peak energy of the gamma ray emission, shown here on the y-axis. But there are some outliers, which you can see at low energies. And so just by definition, these are called low luminosity gamma ray bursts. You can see that some of them also have very low peak energies, and so that's why they're sometimes called X-ray flashes. So what are these things? They are definitely related to classical gamma ray bursts because they share the same type of supernova, but the structure of the outflow seems to be different. It seems to be very wide, not highly collimated. They also have luminous X-ray and radio emission, as you'd expect from a relativistic explosion, but it's not clear what the relationship is to classical GRBs. These have been known about for a long time. One of the most famous examples was GRB 060218 associated with supernova 2006 AJ. And one of its distinguishing characteristics was this early flash, which started in the soft X-rays, as you can see in this figure, and then as it cooled, passed into the UV and optical bands. This has been widely interpreted as a relativistic shock breakout event. The thing that is puzzling is that if you model this event, as several groups have done independently, you infer a breakout radius that is orders of magnitude larger than what you should get from a stripped envelope supernova progenitor. In my opinion, there's been no satisfactory explanation for this. So this is sort of intriguing. And if you take the early light curves from other low luminosity GRBs, and now there's been a kind of resurgence in this area because of the launch of Einstein probe, you see that this early blue emission is quite ubiquitous. This is the figure from the work of Jado Vale. And this is just showing, so on the top row, you have some of these low luminosity GRBs. On the bottom right, 2 well-studied objects discovered by Einstein probe as X-ray flashes. And you can see that within the first couple of days, there can be very luminous and very blue emission, presumably from a similar relativistic shock breakout mechanism. So what does that mean? It means that for ULTRASAT, actually, it has great prospects for detecting a huge number of these things. The rate is very uncertain. So what I've put here is a range from sort of the most pessimistic, so just saying every single one of them is like our fastest and least luminous early emission, like 2006 AJ. And then on the more optimistic end, I'm saying every single one of them is like our most luminous and long-lived events, like this Einstein probe event, 2025 KG. So the truth is somewhere in between. We don't really know the luminosity function, but I think it's safe to say that ULTRASAT can really dominate the discovery rates of these sort of relativistic shock breakout events. And this will really help us determine their origin because it's just been slow. The discovery rate of them has been very slow. Okay, the last group I'm going to talk about is something different. So these are transients sort of defined by comparison to their prototype, which was this transient called 802018 COW, or the cow. This event was discovered by Atlas in 2018. And not only does it have a very fast and blue and luminous UV optical transient, but importantly, it has luminous emission across the electromagnetic spectrum. So this plot is showing its SED all the way from centimeter wave radio wavelengths all the way up to the X-rays. And in basically every band, it's orders of magnitude more luminous than classical supernovae. So what are these things? Since then, we've been finding many more of them using ZTF. The total today is something like, I think, 14 events. And for each of these, we identify them optically, but we then follow up with the VLA. We have a longstanding VLA program. And what's kind of remarkable is that the vast majority of the time, you end up measuring a radio light curve that is extremely similar. So the plot on the left shows a collage of radio light curves. The gray dashed lines near the bottom are known sort of strip envelope supernovae, where the radio emission is luminous because of CSM interaction. And on the top, you have dotted lines from gamma ray burst afterglows. And then everything else are these transients similar to 18 Cal, which are sometimes called LF bots. And what you can see is that the radio light curves peak at around the same time. They're all clustered within an order of magnitude or so in luminosity. And it's very, very different from core collapse supernovae, which can vary by orders of magnitude in peak luminosity and in time to peak. So that implies a similar circumburst environment at the time the transient occurs. And then on the right-hand side, you are seeing the stellar mass versus star formation rate of their host galaxies. And every single one of them is in a star-forming galaxy. So I think the implication is that they have something to do with massive stars, which immediately disfavors some of the proposed models in the literature. Another remarkable feature, we've only seen this in one of these events so far, but it's very hard to look in a systematic way. At least one of them exhibited these minutes duration flares at supernova luminosities 10s to 100 days after the initial transient. So this is probably our best observed flare. This was observed with a high-speed photometer on the 2.4 meter Thai National Telescope. I don't have time to talk much about this. These flares are red, non-thermal, and so probably from a relativistic outflow, but somehow it can persist for tens of days, as opposed to, say, a gamma ray burst, where they can only go on for maybe at most a day. All right, so what are these things? There are many models proposed in the literature. I think it's pretty clear that they have to be associated with massive stars personally. And so these models for example, intermediate mass black hole tidal disruption events, I think they have to explain why all these things would be in star-forming galaxies. I think one of the most popular models at this point, because of the combination of star-forming galaxy and very consistent circumstellar medium sort of structure, is some kind of merger, because then you could produce the sort of consistent circumstellar medium timed with the terminal explosion. But ultimately, telling the difference or testing all of these different models requires obtaining certain kinds of data that have been very difficult for us to obtain, because we typically discover these somewhat late in their evolution. So the optical is kind of is really not where the main action is. These are really very UV luminous transients at the earliest times. But because we're finding them in the optical, we have a lot of false positives, and we typically don't really identify them until maybe a week or sometimes even 2 weeks later. They are extremely luminous, as I said, in the UV band. This is one of the best observed objects in the UV. And they all have extremely similar UV light curves, actually, as far as we can tell. And so I'm just assuming the sort of typical UV light curve, and just taking that and estimating rate with ULTRASAT. you get 30 per year discovered in the very high cadence fields, so the 5-minute cadence fields, and then hundreds per year discovered in the day cadence fields, all the way out to a redshift of about 0.8. So that would be a total game changer. And with ULTRASAT, also its long stares in the high cadence region, we have a natural way to look for short time scale phenomena extending tens to hundreds of days after the initial transient event. And as I said, right now, that's very difficult for us to do systematically. Okay, so I think I'm pretty much at the end of my time. I was asked to also address some of these workshop questions, but I think what I'll do is just leave this up and take any questions that you have.
All right, thanks, Anna, for the awesome talk. So questions, again, preference to early career researchers for the first question.
Thanks for the great talk, Anna. I was wondering, for 2006 AJ, you mentioned that the radius is a bit unbelievable. So I was wondering, do you have an idea of an explanation? Do you think maybe this is from a jet potentially and not shock breakout? I'm just curious what you think.
Yeah, so genuinely, I think this large inferred breakout radius is a great mystery. Initially with 2006 AJ, the proposal was that, the star loses mass shortly prior to core collapse. And so you have this dense, optically thick material around the star. And so you're just seeing the breakout from that. But the fact that this is seen consistently in so many of these other events, to me, it sounds, so why did it lose mass shortly prior to core collapse? And why does that only happen in a subset of these events? So I don't know, somehow it feels to me a bit similar to what we found with 18 Cow and these other events, where you need to, in the same way, produce the circumstellar medium timed with the terminal event. And so perhaps that also suggests that these are somehow triggered by mergers of some kind. But I think that is mysterious.
Yeah.
Hi, Anna. About the low luminosity GRBs, can you explain why those optical light curves, many of them dipped and then rose again? Is that just the afterglow and then the supernova?
Right, that's what we were just talking about. So they have two. So the second part is a supernova, but then the first part is usually interpreted as some kind of shock breakout cooling event. But the weird thing is that if you see that in the optical, that means the radius has to be pretty large. Yeah, much larger than you'd normally expect for this kind of progenitor.
I guess I have a quick question. So in this circumburst or circumstellar environment around these like LF bots, the ones where the progenitors are massive stars, does it seem like the density distribution in it is like R to the -2? So is some gradual smooth mass loss rate, or is it more like, is it a thin dense shell that's some more bursty mass loss?
Yeah, that's a good question. So there aren't that many events where the density profile has really been measured, but for the ones where it has been measured, you can do this with radio observations. It seems to be steeper than an R to the -2. And so that's been interpreted as meaning that there's some mass loss event that happens in an abrupt way, right timed with the terminal event. I would just add the caveat that there are orders of magnitude uncertainties in these measurements in the radio band, but I think the profile itself is fairly robust. Yeah.
Oh, cool. So that seems roughly consistent then with that merger.
Yeah, exactly. Yeah.
All right. Any more questions? Any questions online?
I don't see any, but if you want to post a question online.
There's one from Monica back there.
Hi, Anna. Very nice talk. Just one quick question. You mentioned that the LF boats are mostly found in star-forming galaxies. What's the typical offset?
Several kiloparsecs.
Okay, thanks.
So I know on the red supergiant side, and I think even like yellow supergiant side, people are showing that when you start really modeling convection properly, maybe stars are bigger and more extended than we thought. Is that something that is, I guess, on scale that could affect this type of thing? If, I don't know, are maybe things are more extended than we previously thought, and it's not necessarily CSM, but like a bigger envelope, or do these really have to be compact in order to get some other observables we see?
Yeah, that's a good question. So for the low luminosity GRBs, yeah, I don't know if that's something that's expected in these stripped stars. I'd have to, maybe we could chat about that at the break.